Yeah, Assalamualaikum. This is your Thermodynamics 2 class. Today is lecture number 21. Okay, so can anyone confirm what's beyond my screen right now?
जी sir, lecture number 21.
Oh, thank you so much. Okay, so before starting the lecture, I will again remind you for the quiz timing. Okay, so you can see in this snapshot. Okay, so tomorrow the quiz is at the same time for all the section. So it will open at 10 a.m. and close at 6 p.m. So you will get 10 minutes once you click for the attempt. Okay, so the procedure for the quiz is the same. Okay, so and also the pattern, which is MCQs. So first five questions are MCQ based, and then one is the short question. Okay, and the short question is basically one small numerical, but you can easily solve by just putting one formula. So it is not difficult if you have basic understanding of the gas power cycle. Now coming towards the course, so the topic that is included in this quiz is Otto cycle, Carnot cycle, gas power, and then there will be diesel cycle, and then fuel cycle. Okay, so these are the topic you have to just revise, and I think you can easily attempt all the questions. Okay, and you can easily get full marks in it. So if you have any question, you can ask me, and then we will start with the lecture.
सर न्यूमेरिकल में कोई एक्सटेंसिव सॉल्विंग तो नहीं करनी होगी ना, बस एक दो फॉर्मूले लगा के आंसर उस तरह कहीं है ना?
जी जी बिल्कुल एक फॉर्मूला है और मेन इंपॉर्टेंट पॉइंट इज कि फॉर एग्जांपल इफ द आंसर ऑफ द क्वेश्चन इज फॉर एग्जांपल आई एम जस्ट सेइंग 9.30 okay, so you have to just plug the value 9.30 exact value, not in term of figure. For example, I can just show you over there. Okay, so for example, if your answer is 9.30, so you just have to mention this answer. Do not write that it will be 9 or something like this, okay? Because it is stored in the system, so it will just read in the numeric form. Okay, and make sure you have to put the exact value. Do not write if 9.30 is the answer, do not write 9.25 or also do not write 9.35. Okay, so you have to just plug the exact value, and it is just one word. Okay, now I think one number. Okay, so you just have to, and it will be just taking for example, I can say you have to measure the efficiency of dual cycle, and all the data is available. So you just have to look for the efficiency of dual cycle equation and plug the value, and you will get the answer. Okay, so this is the just example that how this question, which is a short question, you can attempt. Okay.
सर कितने डेसिमल प्लेसेस तक आंसर लिखना होगा अगर ऑटोमेटेड चेकिंग है?
Just two. Okay, so just for example, just I say that 9.30, so you can just get an idea that some answer will be like this. Okay, so it can be any answer. Okay.
Okay.
Okay, so now coming towards the lecture 21, which is chapter 15 again. Okay, and I hope this is our last lecture related to the chemical reaction. Okay, so in the previous class we already talked about how to calculate air fuel ratio, how to calculate mass fraction, gravimetric analysis, how to perform molar analysis. Okay, so these are all the basis thing. So now we will just coming towards the new topic, which is theoretical and actual combustion process. Okay, so in order to analyze the actual and actual combustion process and theoretical combustion process, so first we will have to understand some basic terms. Okay, so by which you can easily solve the problems. Okay, so first term is the complete combustion. Okay, so when we have to say that our chemical reaction is a equation that is related to the complete combustion. Okay, so if all the carbon in the fuel burn to CO2, all the hydrogen burn to H2O, and all the sulfur burn to SO2. Okay, so if you can not see any element that is carbon, H2, carbon monoxide, and OH in the product side, so it's mean this is a complete combustion equation. However, if you can see these components, for example, carbon, H2, carbon monoxide and OH. In the product side, so it's mean this is the chemical equation for the incomplete combustion process. Okay, so this is the first understanding you can develop, that how you can judge the complete and incomplete combustion equation. Okay, so now coming towards the reason for the incomplete combustion. Okay, so I already, if you can remember, that I already told you that for the oxidizer, which we use air as oxidizer with the combination of fuel. Okay, so if we supply less amount of air, and also if we supply less amount of air, so it will result in the not accurate combustion. Okay, so the accurate combustion means that we are getting incomplete combustion. Okay, so the first cause is insufficient supply of oxygen. Second thing is insufficient mixing in the combustion chamber during the limited time that the fuel and oxygen are in contact. Okay, then there is a third term, dissociation. Okay, dissociation means that breaking of the molecule into other molecules. Okay, so these are the three reasons for which we get the incomplete combustion. Okay, so for example, if we have fuel, okay, any fuel, and then we have air, okay, and we send it to the combustion chamber. Okay, so you already know we get some CO2, we are getting H2O in the product. We have excess O2 in component of the fuel are burned to completion. Okay, so in this you didn't see any carbon, any H2O and carbon monoxide and OH in the product side. Okay, so this you can say this is a complete combustion equation. However, in some cases the excess O2 is also, we can say, it is a incomplete combustion process, but these depend upon the case to case. Okay, so we will discuss in the problem as well. So oxygen has much greater tendency to combine with hydrogen than it does with carbon. Therefore, the hydrogen in the fuel normally burn to completion, forming H2. So these are some terms. Okay, so now coming towards the some more terms to analyze the actual combustion or theoretical combustion process. So another term is stoichiometric or theoretical air. Okay, so this term, I think stoichiometric, you already are familiar with the chemistry courses. Okay, so here what is the meaning of the stoichiometric and theoretical air? So it is basically the minimum amount of air needed for the complete combustion of fuel, and also it is referred to as a chemically correct amount of air or 100% theoretical air. So for example, if I say that theoretical air, I am supplying theoretical air with the fuel. Okay, so this is the meaning. The meaning of the statement is that I am supplying 100% theoretical air. Okay, because the minimum amount required to complete the combustion is 100% theoretical air. Okay, so you have to supply. Then stoichiometric or theoretical combustion. So the ideal combustion process during which fuel is burned completely with theoretical air. Okay, so it's mean that the combustion process, if I am supplying 100% theoretical air with the fuel, so this is theoretical combustion. Okay, because I am supplying the minimum amount with the fuel. Then there is a term excess air. So the amount of air in excess of stoichiometric amount, usually expressed in term of stoichiometric air as percent excess air or percent theoretical air. Okay, so excess air we will see at this point. Okay, so what is the meaning of excess? So right now you can just note it down that the amount of air in excess of the minimum amount we call as a excess air. Okay, for example, if 100% theoretical air is required for the complete combustion and I am supplying 110% or I am supplying 10% more air, okay, so it's mean I am supplying excess air to the theoretical amount. Then there is a deficiency of air. Okay, so the amount of air less than stoichiometric amount. So minimum amount is 100%. So any amount you are supplying less than stoichiometric amount, which is the minimum amount. So it is expressed as the percent deficiency of air. Then there is a term equivalence ratio, the ratio of actual fuel air ratio to the stoichiometric fuel air ratio. Okay, so this we will see with the problem as well. Also, for example, I want to find the equivalence ratio for some chemical reaction. Okay, so for this I need two different chemical equation. So first chemical reaction is based on the actual combustion process, where I get the actual fuel air ratio, and then I have to use another chemical reaction equation, which is a stoichiometric equation, okay, for the combustion process. Okay, so for this process, for finding the equivalence ratio, we need two chemical equation. Okay, so now here, for example, in the problem statement is mentioned that I am supplying 50% excess air with the fuel. Okay, so this means that the theoretical air I am supplying is 150%. Okay, so 150, how it is 150%? So 100% is the minimum amount required to complete the combustion, and then I am giving 50% excess air. So total will be 150% of theoretical air. Similarly, for example, I am saying that in the as oxidizer there is 200% excess air. Okay, so the term means 300% theoretical air. So 100% is the minimum amount and 200% is the excess amount. So if you can combine, it will be 300%. Okay, so now here, for example, if I can say 90% theoretical air, okay, so this term means 10% deficiency of air, because 100% is required amount of air for the minimum amount of air for the complete combustion. So if I am supplying 90% theoretical air, so it's mean I am supplying 10% deficiency of air for the combustion process. Okay, so this is the thing which you have to understand first before we can go towards the problem session. Okay, so now here there is one example for the complete combustion. So for example, I have CH4, then some air, and it turns out to be CO2, H2O, N2. So if you can notice, there is no unburned fuel, there is no free oxygen in the product. Okay, so this is the complete combustion equation. Okay, so you cannot see any component such as carbon monoxide, okay, in the product side. So the complete combustion process with no free oxygen in the product is called theoretical combustion. Okay, and also it is called the stoichiometric combustion, or this equation is also for the stoichiometric reaction. Okay, so for example, if I have to find the equivalence ratio, so I have to find stoichiometric fuel air ratio by using this type of equation, and for actual fuel air ratio we can use actual combustion equation. Okay, so just give me 1 minute. Okay, so these we already discussed what is the complete combustion, so you have to go through it by yourself. Okay, so I already explained to you. Then there is an incomplete combustion. Okay, so this also we already discussed that there is carbon H2, carbon monoxide, and OH in the product side, so it is called the incomplete combustion equation. Okay, so this also we already discussed what is the stoichiometric or theoretical air. Okay, so this is for your study purpose, so you have to go through by yourself so that you can understand. Okay, so now here there is one important point, that in actual combustion process it is common practice to use more air then the stoichiometric amount to increase the chances of complete combustion. Okay, so this is what we have practiced when we are trying to burn the fuel. So every time we try to supply more air so that the chances of the complete combustion will increase. Okay, so and rest of all the story which is written over there. So I already explained that what is the meaning of 50% excess air, what is the meaning of 200% excess air, and what is the meaning of okay, deficiency of air. Okay, so 0% excess air mean 100% theoretical air. Okay, so this is the same thing which I already explained. Okay, so now coming towards one question. So you have to read the problem statement first, and then we will solve how to solve it. Okay, so in this question it is mentioned ethane is burned with 20% excess air. Okay, so 20% excess air, it means we are supplying 120% theoretical air during a combustion process, and figure is shown over there. So the reactant and products, assuming complete combustion and total pressure of 100 kilopascal. So you have to determine air fuel ratio by using this data. And this is, I think, example 15-2. So you have to note it down, and then I will try to solve it. Okay, so first we will start with the chemical equation. Okay, so this chemical equation, every time if you see this type of question in the exam, it will be provided to you, okay, with the problem statement. So you do not need to remember this, how to build the equation. Okay, so for example, this is the equation. Okay, so here in this question, if you can notice that, for example, this chemical equation is mentioned with your problem statement. So here 1.2. Okay, so where this 1.2 come from? This come from basically the problem, the data which is available, that we are supplying 20% excess air. So which the meaning is 1.2 into some coefficient. Okay, so this coefficient is basically the stoichiometric coefficient. Okay, so first step in order to solve the air fuel ratio by using this equation, you have to find this stoichiometric coefficient. Okay, and how you can find this stoichiometric coefficient? If you can simply apply the balance of oxygen, okay, for this chemical equation, you can easily find this stoichiometric coefficient, which is ATH. Okay, so for example, I can just apply the balance for O2. Okay, so in the reactant side, we have 1.2 stoichiometric coefficient is equal to 2, which is in the product side, plus 3 by 2 because it is the monatomic oxygen on the product side, and then 0.2 into stoichiometric coefficient. Okay, so if I can solve this equation for ATH, it will be equal to 3.5. Basically, this TH means theoretical. Okay, and A is just a letter, we can denote with any. Okay, so we call it as a stoichiometric coefficient. So the value of stoichiometric coefficient become 3.5. So now our equation become complete. Okay, so this equation you will be provided with the problem statement, and rest of the procedure you have to solve it by yourself every time. Okay, you can see this type of question in the exam. Okay, so now our equation become by which we can solve for air fuel ratio, so which is C2H6 plus 1.2 into 3.5. Okay, so you can multiply 4.2 will be the answer, and O2 plus 3.76 into, and it gives 2 CO2, 3 H2O, and 0.7 O2. So I will just multiply 0.2 with 3.5, and it gives 0.7 O2 and plus 15.79 N2. Okay, so 1.2 into 3.76 into 3.5. Okay, so it will be 15.79 N2. So this is our combustion equation by which we can easily solve the air fuel ratio. Okay, so air fuel ratio, you already know, mass of air over mass of fuel. Okay, and here you can say number of mole of air, molar mass of air, number of mole of fuel, molar mass of fuel. Okay, so how many number of mole of air in this equation, which is 4.2 into 4.76. So 1 plus 3.76, which is equal to 4.76. Because air is the collective. Okay, so this is complete called as a air. And then molar mass of air, which is 29, and number of mole of fuel is 1. Okay, so if you can notice over there, and then the molar mass of fuel is 30. Okay, so you just have to calculate the molar mass C2 and H6, and you can get the value, which is 30. And if you can divide these two values, you will get the air fuel ratio, which is 19.3 kg of air per kg of fuel. Okay, so this is the air fuel ratio if we are supplying some excess amount of air. Okay, so this is the procedure when the data is available that you are supplying excess amount, and also you can solve the same question if I can say that I am supplying 10% deficiency of air. Okay, so here you can just replace with 0.9. Okay, if I am saying that it will be the 10% deficient air. Okay, so if you have any question, you can ask me, and then we will go towards the next question. So you can note it down, and then we will try to solve another question. So now coming towards the next problem, which is from your book, and it is 15-31. So you have to first read the statement. A certain coal has the following analysis on mass basis: 82% of carbon, 5% H2O, 2% H2, 1% O2, and 10% ash. Okay, so collectively we can say it will be the coal. Okay, and the coal is burned with 50% excess air. And what you have to determine, air fuel ratio. Okay, so you have to note it down these percentage and the data, and then we will see that how to solve this stuff. Okay, so for example, I can give the combustion equation with this problem statement. So the combustion equation is C. Okay, so this I will explain after this what is NCU. Okay, so for example, this chemical equation is mentioned with your problem statement. Okay, so collectively it is mentioned that our coal consists of carbon, H2O, H2, O2 and ash. Okay, so collectively it is called fuel. Okay, so this is our fuel, and then we are going to supply 50% excess air. So it's mean 1.5 into stoichiometric coefficient into air. Okay, so this is air, O2 plus 3.76 N2. Okay, so if we can react these two things, okay, so it will give x mole of x mole of CO2 and then y H2O. Okay, so these are basically the moles plus 0.5 theoretical amount of air, your stoichiometric coefficient O2 in plus 1.5 into 3.76 stoichiometric coefficient N2 plus H. Okay, so this is available with your problem statement. Okay, so first step is because the mass balance, mass basis, the percentage is given in your problem statement that this is the percentage of carbon, this is the percentage of H2O, and then H2 and O2, which is available with the problem statement. So first thing is you have to find this number of mole of carbon, number of mole of H2O, number of mole of H2, number of mole of O2. Okay, so this is the first step you have to perform. Okay, you can see this type of question. Okay, so number of mole of carbon come from mass over molar mass, and you can say it is called carbon. Okay, so before this you can just consider that the fuel is 1 kg of coal. Okay, so that it will be easy for you and analyze the required thing, which is the air fuel ratio. Okay, so for example I am supplying 1 kg of coal with the 1.5 with the 1.5 theoretical air. Okay, and these two things react in the combustion chamber. Okay, so here in the question it is mentioned that the carbon has 82% of the mass. Okay, so 82% on the mass basis. So it means that 0.82 is the mass of the carbon. Okay, so molar mass of carbon you can easily find from the thermodynamic table, or you can remember it. It is 12. Okay, and you can solve it, and it will be equal to 0.0683 kilomole. Okay, so I will just find the NC here. So similar procedure, you have to find the number of mole of H2O. So mass of H2O over molar mass of H2O. Okay, so mass, which is mentioned in your problem statement, we are giving 5% that your coal consists of 5% of H2O. Okay, so it means it is 0.05 divided by 18, and if you can solve it, it will be equal to 0.0028 kilomole. Okay, so similar procedure, you have to find number of mole of H2. So mass of H2 over molar mass of H2. So mass, which is mentioned at 2% of H2. Okay, so you can say 0.02 over molar mass of H2, which is 2. and if you can divide it, it will be 0.01 kilomole. Okay, and last thing is number of mole of O2. So mass of O2 over molar mass of O2, and mass of O2 is 0.01, which is mentioned 1% of oxygen, and divided by 32, and it will be equal to 0.00031 kilomole. Okay, so now we have all the moles associated with the fuel. Okay, so similar procedure, you can first thing is you can put these number of mole into this equation, so that there will be one chemical equation by which we can solve other parameter, which is x, y, theoretical coefficient, stoichiometric coefficient, and then okay, so these are the three coefficient which we have to find. Okay, so for example, your equation now become 0.0683 carbon plus 0.028 H2O. Okay, so just I am putting the value of number of moles which I already find in the previous step, plus 0.01 H2 plus 0.00031O2 plus ash, and this is your fuel, and you are adding 1.5 critical coefficient O2 plus 3.76 N2, and it's give x mole of CO2, y mole of H2O, 0.5 into critical coefficient O2, and plus 1.5 into 3.76 ADH N2 plus ash. Okay, so this is the equation of your combustion reaction. Okay, so now here you have to find the x and y coefficient by just balancing the equation, mass balance of the carbon, of H and O2. Okay, so you can easily find these three coefficients, which is x, y, and stoichiometric coefficient. So you have to note it down, and then we will move towards the next part. Okay, so now we have to apply the mass balance. Okay, so mass balance, for mass balance you have to correlate with the combustion equation, which I already wrote in the previous slide. Okay, so I am not going to write the equation again. Okay, for example, I can apply the mass balance for carbon. Okay, so you have to look for the equation by yourself. Okay, so in the reactant side we have 0.0683, and in the product side we have x carbon. Okay, so from here we can say x is equal to 0.0683. Similar thing, you have to apply the mass balance for H. Okay, so in the reactant side we have 0.028 into 2 plus 0.01 into 2. Okay, so these are available in the reactant side, and 2y at the product side. And then we have O2. So O2 in the reactant side we have 0.28 y by 2, because the monoatomic oxygen is available at the reactant side, so we have to divide with the 2 plus 0.00031. This is also on the reactant side, and then 1.5 ATH at the reactant side, and it is equal to x plus y by 2 plus 0.5 into stoichiometric coefficient. Okay, so we have the value of x and y with us, okay, from the previous step. Okay, so here you can easily find the value of y, which is equal to 0.00128. Okay, so now we have all the values, so just simply you can put in the mass balance of O2 and the ATH value will be 0.073. Okay, so this comes from the mass balance. So now I can put all these values x, y and ATH in the chemical equation, which I already wrote in the previous slide. Okay, so now your chemical equation for the combustion process become 0.0683 carbon plus 0.0028 H2O plus 0.01 H2 plus 0.00031 O2 plus ash. This is our fuel, and plus you are supplying with the 1.5 ATH, so 1.5 into 0.073. Okay, so it will be equal to 0.1095 O2 plus 3.76 into, and in the product side we have x amount of CO2, so x value is 0.0683 CO2 plus we have y amount of H2, so y value is 0.0128 H2O plus we have 0.5 into theoretical coefficient, which is 0.5 into 0.073. Okay, so this is 0.0365 O2 and plus 0.4117 N2 and plus the remaining ash. Okay, so this is the chemical equation, okay, for the data available in your problem statement. Okay, so now here we can easily find the air fuel ratio. Okay, so air fuel ratio you already know, it is equal to mass of air over mass of fuel. Okay, so here we can say number of mole of air into molar mass of air. Okay, so from here we can get the mass of air. Okay, so if you can remember that we have already considered that the mass of fuel we are supplying is 1 kg. Okay, so you can directly put 1 kg because we are already considering that we are supplying mass of fuel is equal to 1 kg. Okay, so here you can just multiply number of mole of air, which is 0.1095. Okay, so if you can notice over there, so this is your number of mole, and then multiply with the 4.76 into molar mass of air, which is 29, and divided by 1. Okay, so if you can just solve it, it will be equal to 15.1 kg, okay, of air per kg of fuel. So this is your air fuel ratio for this type of problem. Okay, so if you have any question, you can ask me, and we will note on the solution, and then we will go towards the next question.
सर ये 0.1095 कौन सा है
0.1095 कैसे है आज
सर
मैं आपको बता ओके आपने पिछली क्वेश्चन नोट की थी जिसमें हमने मेंशन किया था कि यहाँ पे जो आपके पास है वो है 1.5 वी आर सप्लाइंग 50% एक्सेस एयर एंड देन stoichiometric coefficient O2 plus 3.76 N2. Okay, so simply I have put the value of stoichiometric coefficient, which is 0.073. Okay, so if you can multiply 1.5 with 0.073, it will be 0.1095.
ओके सर
Okay. Okay, so we will take 10 minutes break and then we will again join after 10 minutes. So coming towards the next problem, which is example 15-4 from your book. Okay, so you have to read the problem statement first. So octane is burned with dry air. The volumetric analysis of product on dry basis is mentioned. So CO2 10.02%, O2 5.62%, carbon monoxide 0.88%, and N2 83.48%. So two things you have to find out using this setup: the air fuel ratio and percentage of theoretical air use. Okay, so in this question it is not mentioned that how much air you are supplying. So rather you have to find the percentage of theoretical air. Okay, so you have to note down all the required things, and then we will see at how to solve it. So again, coming towards the chemical equation, which will be provided with the problem statement. So C8 H18 plus A into O2 plus 3.76 N2. It gives number of moles is given in your question, which is 10.02 CO2. Okay, so we are considering that 100 kilomole of dry air for the convenience purpose. Okay, so here we can say 0.88 CO plus 5.62 O2 plus 83.48 N2 plus B into H2. Okay, so this equation will be provided with your problem. Okay, so now here, first thing is to apply the mass balance definitely, because we have many coefficient, unknown coefficient with this chemical equation. So XA, similarly we have B. Okay, so we have to apply the mass balance first for N2. So mass balance for N2 is 3.76 into A, which is equal to 83.48, and at the product side. Okay, so from here I can find the value of A, which is equal to 22.2. Similarly, you have to apply the mass balance for carbon, okay, so that you can find the value of X. So 8X is at the reactant side and 10.02 in the product plus 0.88. Okay, so from here I can find the value of X, which is equal to 1.36. And next we have to find the value of B. So for B we can easily apply the balance for the H. So for H balance it is 18X on the product side, on the reactant side, sorry, and in the product side we have 2 into B. Okay, so from here we can find the value of B, which is, because X is known to us, so it's just we have to put the value of X over there, and it will be equal to 12.24. Okay, so now we have all the unknown coefficient, so we can simply put that value of coefficient into the chemical equation. Okay, so this chemical equation become 1.36 C8 H18 plus 22.2. Okay, so just I have got the value of A, O2 plus 3.76 N2, and which give 10.02 CO2, 0.88 CO plus 5.62 O2 plus 83.48 N2, and plus 12.24 H2. Okay, so this is the required equation after putting the value of unknown coefficient. Okay, so here for our convenience also, so we can just say that we have to make this equation for 1 kilomole, okay, rather than, because this is for 100 kilomole. Okay, so what you have to do is you just have to divide 1.36, okay, because so that we can make 1 kilomole of fuel is supplied with the oxygen. Okay, so you have to divide 1.36 throughout this equation for all the terms. Okay, so then we will get the one combustion equation for 1 kilomole of fuel. Okay, so then it is easy for us to analyze the fuel erosion. Okay, so you have to note it down, and then I will write the next equation. Okay, so after division of 1.36, our equation become C8H18 plus 16.32 O2 plus 3.76 into, and the product side we have 7.37 CO2 plus 0.65 CO plus 4.13 O2 plus 61.38 N2 plus 9 H2O. Okay, so this is the equation of our combustion reaction. Okay, so now by using this equation, you have to find the part A. So part A is to find air fuel ratio. Okay, so air fuel ratio, which is equal to mass of air over mass of fuel. Okay, so here you have number of mole of air, molar mass of air, number of mole of fuel, molar mass of fuel. Okay, so number of mole of air, if you can notice over there, 6.32 into 4.76. So here 16.32 into 4.76 into molar mass of air, which is 29. Number of mole of fuel is 1 now, and now you have to calculate the molar mass of fuel, which is 114 C8H18. Okay, so you can divide these two things and you will get the air fuel ratio, which is 19.76 kg of air per kg of fuel. Okay, so now this is the first part, and now coming towards the second part. So in the second part, our required thing is to find percentage of theoretical air use. Okay, so because we have to find how much excess air we are going to supply. We are supplying in this chemical equation. Okay, so for this, what we have to do is, we already know that the percentage theoretical air is equal to mass of air, and you can say it will be actual and mass of air theoretical. Okay, so where these values come from? Mass of air actual directly come from this chemical equation. Okay, so because this is the actual chemical reaction, then we have to find the mass of air by using the theoretical equation as well. Okay, so where the theoretical equation come from? So this equation I will also provide with the problem statement, that this is the stoichiometric combustion equation, or either it will be the theoretical combustion equation for this chemical phenomenon. Okay, so for example, the stoichiometric equation is C8H18 plus stoichiometric coefficient into O2 plus 3.76 N2, which give 8 CO2 plus 9 H2O plus 3.76 stoichiometric coefficient into N2. So here you can easily judge that this is the theoretical combustion equation, because if you can notice, there is no free element which is carbon, hydrogen, and other free element which is carbon monoxide. So you cannot see anything in the product side, and also you do not see any excess oxygen over there as well. Okay, so it means this is the theoretical combustion equation or stoichiometric combustion equation. Okay, so now here, first thing you have to find the value of this stoichiometric coefficient. Okay, the stoichiometric coefficient you can easily apply mass balance of O2. So mass balance of O2, product side ATH, which is critical stoichiometric coefficient, and then 8 on the product side, and then plus 4.5 will be equal to 12.5 of value for the stoichiometric coefficients. So now you just put the value of 12.5 over there. So this is 12.5. Okay, so now we can easily find the mass of air theoretical by using this chemical equation. So mass of air actual will be equal to 16.32 into 4.76, and then molar mass of air is 29 divided by, now here we have 12.5 because this is the theoretical one, and then 4.76, and mass of air, molar mass of air is same 29. Okay, so this 29 can be cancelled. Okay, so now here if you can solve, you can just take the ratio of these two things. So you will easily find that your percentage theoretical air become 131%. Okay, so it's mean, so I can just write over there the answer, which is 131% by solving this. Okay, so it's mean we are supplying 31% excess air in this chemical reaction. Okay, so this is the solution for this type of question if you have to find the percentage theoretical air by using the available data. Okay, so if you have any question, you can ask me, or otherwise you can note it down, and then we will see how to solve next question. So now here there is some information just for the information. So the predicting of the composition of product is relatively easy when the combustion process is assumed to be complete. Okay, so with the actual combustion process, it is impossible to predict the composition of product on the basis of mass balance alone. Okay, so then how we can find the composition of the product for the actual combustion process? So the on the only alternative, we have to measure the amount of each component in the product directly by using the experimental procedure. Okay, and the experimental procedure or the device which we can use to find the composition of the product okay, for the actual combustion process is Orsat gas analyzer. Okay, so this is just for your information which device we have to use for finding the composition of the product for the actual combustion process, so which is Orsat gas analyzer. Okay, so now coming towards two more important terms, okay, related to the combustion process, okay, because if there is a heat involved, okay, so in the chemical reaction, because you already know, either there will be a chemical reaction where there will be a rejection of heat, okay, and where you are supplying some heat, okay, so there will be involvement of enthalpies, okay, so and in the chemical reaction, okay, so we already know there will be different molecules, and molecule possess energy in various forms. So sensible and latent energy, so which is associated with the change of state, chemical energy associated with the molecular structure, nuclear energy which is associated with the atomic structure. Okay, and during a chemical reaction, some chemical bonds that bind the atoms into molecules are broken and new ones are formed. And due to these, the chemical energy associated with these bonds in general is different for the reactant and the product. Okay, so this is some important point over there. Okay, and then you already know when the existing chemical bond destroyed or new ones are formed during the combustion process. So usually a large amount of heat is absorbed or released. Okay, and energy change of system during a chemical reaction is due to change in state, that is pressure and temperature, and a change in chemical composition. So we can just represent change in energy of the system, which is equal to change in energy for the state, okay, so which is dependent on pressure and temperature, and then change in energy for the chemical composition. Okay, so these are two things from which we can find the change in energy of the system. Okay, and when the product formed during a chemical reaction exit the reaction chamber at the initial state of the reactant, delta E state is 0. Okay, so this is just information for you, and the energy change of the system in this case is just due to the change in chemical composition only. Okay, so this is just we are talking about when the product form exit the chemical exit the reaction chamber. So now coming towards the definition of enthalpy of formation and enthalpy of reaction. Basically, enthalpy of reaction is also called enthalpy of combustion. Okay, so this we will discuss later. The standard enthalpy of formation is the change in enthalpy that coexists with the formation of 1 mole of compound from its element. Okay, so from the definition you can easily check that. For example, there is carbon, there is oxygen, and we will get some CO2, yeah, for example. So standard enthalpy of formation is the enthalpy from which we can define if the carbon combine with the O2 and form some CO2. Okay, and then there is a standard enthalpy of reaction. So enthalpy of reaction or enthalpy of combustion occurring in a system when 1 mole of matter is transformed by a chemical reaction. Okay, so this we will discuss later on also in this coming slide. What is the meaning of these all terms? Okay, so now for the analyzing of enthalpy values for either it will be for any component. Okay, so first thing which is the starting point is to assume some standard reference state. Okay, for example, the standard reference state we can just choose that our standard reference state for the reacting system, that is the combustion process, is at 25 degrees Celsius and 1 atmospheric pressure, which is known as standard reference state. Okay, so whenever you have to calculate, for example, any enthalpy at different point, so you have to compare your enthalpy value by using the enthalpy at the standard reference state. Okay, so which is at the 25 degrees Celsius and 1 atmospheric pressure. And how we can denote standard reference state? So only you have to denote with H naught and U naught. So if you can mention, if you can see this type of notation with the enthalpy and internal energy, so you can easily get at this point we are talking about standard reference state. Okay, so when analyzing reactant system, which is the combustion process, the property value relative to standard reference state must be used. However, it is not necessary to prepare new set of property tables for this purpose. The existing table can be used by subtracting the property value at standard reference state from the value at the specified state. Okay, so this is just example. That for example, the ideal gas enthalpy of N2 at 500 Kelvin relative to the standard reference state becomes, so this is your value of enthalpy at 500 Kelvin, and this is your enthalpy value at the standard reference state, which is 25 degrees Celsius and 1 atmospheric pressure. So you have to subtract these two values and you will get the enthalpy relative to the standard reference state. Okay, so this is the some procedure. Another important point over there is you already noted that in the steam power plants or either in the gas power cycle, we use the enthalpy value as kilojoule per kg. Okay, so for this we can represent with H. However, here it is kilojoule per kilomole. Okay, so if you can see H bar, so it is the meaning is kilojoule per kilomole. Okay, so it is in the molar basis. So the bar represent the that it is in the mole basis.
सर
जी,
ये जो वैल्यूज थी हमें टेबल से देखनी है।
मैं आपको बताऊंगा अभी कि कहाँ से आप इसको वैल्यू कर सकते हैं। यूजुअली ये होता है कि हमारे पास वैल्यूज अवेलेबल हैं, ठीक है। फॉर एग्जांपल N2 की वैल्यू है, फॉर एग्जांपल मैं आपको एयर दे देता हूँ, तो इसकी वैल्यू आप इजीली थर्मोडायनामिक टेबल से फाइंड कर सकते हैं। लेकिन जब हम एंथैल्पी ऑफ फॉर्मेशन निकालेंगे तो उसके लिए हमारे पास डिफरेंट टेबल्स हैं, जो कि हम अभी देखेंगे तो उसकी वैल्यूज हमने कहाँ से निकालनी। ओके, सो दिस कम फ्रॉम द थर्मोडायनामिक टेबल।
ओके सर।
Okay, so here again it is related to enthalpy of formation and enthalpy of combustion. So ignoring any work interaction, the heat transfer during this process must be equal to difference between enthalpy of product and enthalpy of reactant. Okay, so here we represent that Q, which is the heat transfer during this process, is enthalpy of the product side minus enthalpy of reactant. And also this Q we can also call as a enthalpy of combustion. Okay, so this is the other name for the Q. Okay, so the Q is same, enthalpy of combustion is also equal to enthalpy of product minus enthalpy of reactant. Okay, so coming towards the enthalpy of reaction, so we already discussed that it is defined as the difference between the enthalpy of the product at a specified state and enthalpy of reactant at the same state. Okay, however, for the combustion process, the enthalpy of reaction is usually referred to as a enthalpy of combustion. Okay, so the enthalpy of combustion term we specifically use for the combustion processes. However, enthalpy of reaction is a general term. Okay, so that can be used for any type of reaction. Either it will be not a combustion process, so we can represent with the enthalpy of reaction. Okay, so now here the enthalpy of combustion HC represent the amount of heat released during a steady flow combustion process when 1 kilomole or 1 kg of fuel is burned completely at specified temperature and pressure. Okay, so here I just mentioned that HR is equal to HC is equal to enthalpy of products minus enthalpy of reactant, and enthalpy of combustion of particular fuel is different at different temperature and pressure. Okay, so these are some important points. So now here the enthalpy of formation. Okay, so there are so many different fuel and fuel mixture that is not practical to list enthalpy of combustion value for all the possible cases. Okay, so moreover, the enthalpy of combustion is not much useful in case of incomplete combustion. Okay, and it is more practical to have a property representing the chemical energy of an element compound due to its chemical composition at specified state in comparison to the reference state. Okay, so enthalpy of formation is defined as the enthalpy of substance at specified state due to its chemical composition. Okay, so whenever you have to calculate the enthalpy of formation, so the starting point is that the enthalpy of formation for all the stable elements such as O2, N2, H2, carbon is assigned a value of 0. Okay, so this is just a starting point, that if you can see in your product side or in your reactant side, there is O2, N2, H2 and carbon, which is a stable element. So you can just assume over there that your enthalpy value of enthalpy of formation is 0 at for these type of elements. Okay, at the standard reference rate, which is 25 degrees Celsius and 1 atmospheric pressure. So this we will also see in the thermodynamic table, that these values are given in some tables as well, that these values are 0. The enthalpy change during the formation of CO2 forms its element C and O2 at 25 degrees Celsius and 1 atmospheric pressure during the steady flow process was determined to be minus 393,520 kilojoule per kilomole. So it's mean, for example, if we have carbon 1 kilomole and we have 1 kilomole of O2, we send it to combustion chamber, and as it is an exothermic reaction, so energy is released, and you can see there is a negative sign with it. So energy is released, and this is the enthalpy of formation value, enthalpy of combustion value basically, minus 393,520 kilojoule per kilomole of CO2. But however, it is mentioned over there, this is also equal to enthalpy of formation. So how this come to be equal to that enthalpy of formation become equal to enthalpy of combustion in this case? Okay, so this can be easily see, for example, you have C plus O2 and it gives CO2. Okay, so and your enthalpy of combustion is basically enthalpy of product minus enthalpy of reactant. Okay, so if you can notice that in your reactant side, okay, so in your reactant side we have stable element which is O2 and C. Okay, so the enthalpy of formation for these are 0. Okay, and enthalpy of formation of CO2 you can find from the thermodynamic table, which is minus 393,520. Okay, so from here you can easily say that your enthalpy of combustion is equal to enthalpy of formation for this type of scenario. Okay. So we will see that how this value you have to figure it out from thermodynamic table in the coming slide. Okay, so this I already explained to you. Okay, so you have to go through it by yourself. Okay, so the same example is discussing over there. Okay, now here another important point that we already know, that endothermic process has a product having positive enthalpy of formation, and exothermic process has a product with the negative enthalpy of formation. Okay, so this negative and positive sign you can easily judge that either it is an exothermic process or either it will be the endothermic process. Okay, so now another term for the analysis of combustion process is the heating value. Okay, basically heating value and enthalpy of combustion is the same thing. Okay, so we simply say that heating value is equal to absolute value of enthalpy of combustion. So it's mean if any negative sign you can just eliminate because it is the absolute value. Okay, so why we need to define another term which is the heating value? Okay, heating value is specifically used for the fuel. Okay, however, previously heat of enthalpy of combustion or enthalpy of formation you can use for any sort of element, but heating value specifically used for the fuel. So fuel is defined as the amount of, so heating value of the fuel is defined as the amount of heat released when fuel is burned completely in steady flow process and the products are returned to the state of reactants. and the heating value of fuel is equal to absolute value of enthalpy of combustion of the fuel. Okay, so this is the important point over there. So for example, if in the question it is given that the fuel, which is methane, is burned, and the heating or the enthalpy of combustion is mentioned that it is, for example, 400 kilojoule per kilomole. Okay, so you can easily judge that the heating value of that fuel is known to us in the problem statement. So now here, okay, so this we already explained. Okay, so you can just go through it by yourself. Okay, so enthalpy of reaction, enthalpy of combustion. Okay, now here another important term over there. Okay, so heating value we already discussed, that amount of heat released when fuel is burned completely in a steady flow process and product are returned to state of reactants. The heating value of fuel is equal to absolute value of enthalpy of combustion fuel. However, there are two terms associated with this heating value. First is higher heating value and second is lower heating value. Okay, so for example, if there is a fuel and there is air, you have sent it to the combustion chamber and there is some release of energy. Okay, and in the product side you will get H2O. For example, if in the product side you will get the vapor phase of H2O, so if it is in the vapor form H2O, this value of heating value is defined as a lower heating value. Okay, however, in the product side, if H2O is in the form of liquid, so we can call it as a higher heating value. Okay, so this is the only difference, that how you can judge that the value is higher heating value or lower heating value. So you have to just check the phase of H2O in the product. Okay, and then how you can relate higher heating value with the lower heating value. So double HV is equal to LHV, which is lower heating value, is equal to mass of H2O, which is in the product side. Okay, and then latent heat of vaporization. So enthalpy you can easily find from the thermodynamic table. So the same thing you already did in the steam power plant. Okay, so the same table you have to use for HFG of H2O for specified temperature or pressure. Okay, so these are the terms. Heating value is equal to. Okay, another important thing is most of the time heating value you have to represent with kilojoule per kg. However, enthalpy of combustion you can represent in kilojoule per kilomole. Okay, and for the fuel with the variable composition, that is coal, natural gas, fuel oil, the heating value may be determined by burning them directly into warm calorimeter. Okay, so this is the required thing for the high heating value and low heating value. So now coming towards okay, important thing, that how you can look for the values of low heating value, high heating value, and enthalpy of formation. Okay, so for this, simply you have to go to thermodynamic table. Okay, so here it is mentioned in table A26. Okay, and it is mentioned enthalpy of formation. So for example, in your combustion reaction, we have some elements, carbon, hydrogen, or any sort of element. Okay, so you can easily find the enthalpy of formation values by using this column. Okay, so you can notice that the stable element carbon, hydrogen, nitrogen, oxygen have zero enthalpy of formation. Okay, so this is the starting point forward. Okay, so this I already explained in the previous slide. Okay, so this is the value of enthalpy of formation you will easily get from 826. Now similarly, if you want to find the higher heating value and lower heating value of fuels, so the last two columns you can just go through it and you can find higher heating value and lower heating value for all the fuel mentioned in this. Okay, so this is the procedure for finding some thermodynamic properties for the combustion process. Okay, so now we will try to solve one problem so that you will get some understanding of how to find properties from the thermodynamic table. Okay, so if you have any question, you can ask. We will just solve one question. Okay, so this question you have to read it first. Okay, so this is 15-5 from your book. So determine the enthalpy of combustion of liquid octane at 25 degrees Celsius and 1 atmospheric pressure Using enthalpy of formation data from table 826, assume water in the product is in the liquid form. Okay, so from here you can easily judge that if water is in the product is in the liquid form, so the meaning is that it is higher heating value if we can find the enthalpy of combustion. Okay, and if it is mentioned it is in the vapor form, so it means it is low heating value. Okay, so the product and reactants are mentioned over there in the figure. So you have to note down the data and then we will see how to solve it. Okay, so for example, the chemical equation associated with this type of question is C8H18 plus ATH O2 plus 3.76 into, and it will be equal to 8 CO2 plus 9 H2O, and H2O is in the liquid form which is mentioned in the problem statement, and 3.76 stoichiometric coefficient into N. So now this is your chemical equation. Okay, so here our required thing is to find enthalpy of combustion. Okay, so I already told you that enthalpy of combustion is basically in kilomole, kilojoule per kilomole is basically enthalpy of product minus enthalpy of reactant. Okay, so enthalpy of product, if you can notice over there, that we can simply say summation of number of mole in the product into enthalpy of formation in kilojoule per kilomole and formation of product. Okay, so do not confuse where this n comes from. Basically, if you have to calculate the value of enthalpy in kilojoule per kg, you have to multiply mass. Okay, so here I multiply number of mole because your enthalpy value of formation is in term of kilojoule per kilomole. Okay, so that's why the number of mole is multiplied with this term. So then minus summation of number of mole of reactant into enthalpy of formation of reactant. Okay, so now here if you can notice from the chemical equation in the product side, we have, so number of mole, enthalpy of formation CO2 plus number of mole, enthalpy of formation. Okay, so this is in the product side, enthalpy and H2O, and minus number of mole, enthalpy of formation. Okay, and you have to put the value of naught because it is mentioned in the problem that we are talking about the standard values. Okay, so which is the 25 degrees Celsius and 1 atmospheric pressure. Okay, and this is for the C8H18. Okay, so I already told you whenever there will be stable element, so its enthalpy of formations are 0. So this term, and this term has 0 values of enthalpy of formation. So that's why we are not adding these values in the enthalpy of combustion equation. Okay, so you have to just go to table 826 and find the enthalpy of formation of CO2. Okay, so for CO2, you can just check the thermodynamic table, okay, which is 826. So if you can notice the CO2 over there, which is in the gaseous form, minus 393,520. Okay, so this value you have to note it down first, and then we have H2O. Okay, so H2O you have to look for the value in the liquid state. Okay, because it is mentioned in the problem that H2O is in the liquid form. Okay, so H2O and the liquid form So this is the value, which is minus 285,833. This value also you have to note it down. And then we have liquid fuel, which is C8H18. So C8H18 you can easily find over there in octane, and this is in the liquid form, and you can note down the value minus 249,950. Okay, so these three enthalpy of formation you have to note it down from thermodynamic table 826. So after noting down the values, again you have to come to the problem. Okay, so now here, if I can figure it out, what is number of mole associated with CO2, which is 8, and enthalpy of formation, we already see in the thermodynamic table, which is minus 393,520. Okay, this comes from table 826. Similarly, number of mole of H2O in the product side, which is 9, and enthalpy of formation for H2O, which is minus 285,830 kilojoule per kilomole, and minus number of mole of fuel, which is 1, and then the enthalpy of formation of fuel is equal to minus 249,950. So here you can solve it and you will get the value of minus 5,471,000 kilojoule per kilomole of C8H18. Okay, so this is the required thing which we have to find the enthalpy of combustion level. Okay, in kilojoule per kilomole, and if you want to find in kilojoule per kg, so simply you have to divide with the number of mole into molar mass of C8H18. Okay, so you will get the you can easily convert the value into kilojoule per kg, and which will turn out to be minus 47891 kilojoule per kg. And I already told you, if it is your product side, H2O is in the liquid form, so it's mean it is high heating value. Okay, so if I can say in the problem statement you have to find the high heating value, you can simply figure it out that high heating value is equal to 47891. Okay, so minus is not included over there because high heating value is basically the absolute value of enthalpy of combustion. Okay, so this is the required thing in this problem statement. Okay, so if you have any question, you can ask me, and then we will see the next question.
No, sir, no question.
Okay, okay. Okay, so now the question which you have to solve is the same one. So simply, instead of considering that H2O is in the liquid form in the product, you have to assume that H2O is in the gaseous form, and rest of the procedure is same. Simply you have to look for table 826 H2O enthalpy of combustion value in the for the gaseous form, and also in the end you will get the lower heating value instead of higher heating value. Okay, so this question you have to solve, and all the students will get 0.2 absolute marks for solving this question. Okay, so you have noted down, and then we will just stop at this.